Hello everyone, this is the second video for my YouTube channel. The video is containing solved problems on first worksheet of basic mathematics for freshman students. The worksheet is actually prepared somewhere at one of university of our country, which is University of Gondar. And I prefer to start from the second question of the worksheet. As you clearly observe here, question number 2 says, translate the following composite sentences into symbolic form. And I prefer alternatives here. If it is foggy at night, then either John must stay home or he must take a taxi. So that in order to transform this composite sentence into symbolic form, we have to represent first the simple sentence that can form this composite sentence by using that of small letters. So that in this case, let's assume that the first one, that is the first component sentence, that is foggy, will be represented by P, such that it is foggy tonight. Second one will be, which is here, then either John must stay home or he must take a taxi. So that the second question, simple sentence which can be represented by second letter Q will be John must stay at home. Next, from this we have another simple sentence which is he must take a taxi. Therefore this could be represented by R, that is John must take a taxi. Then after representing this simple sentence in this pattern, the symbolic form of the other will be, for example, in the first case, if it says, if it is foggy tonight, that means this one, that it is foggy tonight, is represented by P, so that we have P implies then either John must stay at home or he must take a taxi. So that it is a combination of two sentences which is combined by using that of this one, that is or simply distraction. Therefore this could be enclosed by using that of a bracket. Therefore it must be Q or R, that is John must stay at home or he must take a taxi. Therefore the symbolic form of the composite sentence will be P implies Q or R. Okay, the next question will be question number 3, which is this one, and it says write the inverse, converse and contrapositive of the following statements, and I prefer the sentence to be the first one, that is A, Khartoum is in Kenya only if Addis Ababa is in Djibouti. So in order to have the inverse, converse and contrapositive of this one, we know that generally if we have a logical implication of this one, that simply P implies Q, we know that for this one, if we are given this, for this logical implication, the inverse of this logical implication will be the negation of P implies negation of Q, that is taking only the negative of the if statement in the conclusion. This is the inverse of P implies Q, and this one, that is Q implies P, is the converse of P implies Q, which is obtained by interchanging only the if statement and the conclusion, or simply the then statement. And when I take the inverse of this one, that is the contrapositive, we'll obtain the contrapositive, that is negation of Q implies negation of P is said to be the contrapositive positive of the given logical implication P implies Q. Therefore, depending on this one, we have the same which we are given. The given statement will be Khartoum is in Kenya only if Addis Ababa is in Djibouti is equivalent with if Khartoum is in Kenya, then Addis Ababa is in Djibouti. So that Khartoum is in Kenya is P, that is the F statement, and Addis Ababa is in Djibouti is said to be that is the conclusion, or simply which can be represented by using that of Q. Therefore, depending on this idea, the expected inverse of this statement, for example, will be that is the inverse of this statement would be that is take the negative of both the if statement and the conclusion, that is if Khartoum is not in Kenya, then Addis Ababa is not Djibouti. They hit the inverse of the statement. Or as it is without any changing, Khartoum is not in Kenya only if Addis Ababa is not in Djibouti. They are equivalent. And the next one, that is the converse of the same statement, will be just a statement which is obtained by interchanging the conclusion and the if statement. So that in this case, if Addis Ababa is in Djibouti, then Khartoum is in Kenya. And lastly, the contrapositive will be just the inverse of the converse of this statement. That means if Addis Ababa is not in Djibouti, then Khartoum is not in Kenya. Therefore, these are the inverse, the converse, and the contrapositive of this statement, that is Khartoum is in Kenya only if Addis Ababa is in Djibouti. Okay, the next one is question number 6, that is selected question will be question number 6, which looks like that of this one, and it says for the statement is P, Q, and that of R, show that first one, that P implies Q or R is equivalent to negation of Q implies negation of P and R, or negation of P or R, and C, negation of P implies Q or R is equivalent to, that is the same statement with different, that is negation of R and negation of P. We know that just to check this equivalency, we have two methods, that is first one is truth table, and the other is using that formal definition, that is formal proof by considering the property of the logical connective that we are using just to form these composite sentences. Then when we start from the first one, I think it is better if we use the first method, that is truth table. So that using truth table, we have this one, for example, that is the component statements are, for example, for A, we have P, we have Q here, we have R. And the other will be, that is Q or R, and negation of P or R. Then the last one will be P implies Q or R, negation of Q implies negation of P or R. Then the possibility for the truth values of the component statements will be, since we have three simple component statements, we have to the power of 3 or simply 8 possibilities. All the three will have true truth value. The first two may be true and R can be false. Only the first can be true and the other false. All the three can be false. The first can be false, but the other two can be true. The first two can be true, false, and the third may be true. And the other is the first and the third may be false, and the middle one can be true. And next we have true, false, and true. 1, 2, 3, 4, 5, 6, 7, 8. So that these are all the possibilities for the truth values of the simple statements. Then here, if we consider Q and R, true or true is true, true or false is true again, false or false is false, false or false is also false. And then we have true, 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 then true. Negation of P or R, we have here, we have to consider the negation or the opposite of this one with respect to this element that is R. We have to here, the negation of true is false, false or true is true, false or false is false, false or false is again false, false, true or false is true, true or true is true, true or true is again true, true or false is true, false or true is true. Okay, then in order to fill the truth value of the first simple complex component that is this element, we have to consider this element and this one, and we have to connect these two elements by implication, so that true implies true is true, true implies true is again true. We have true here, but this one is false, so that true implies false is false, false. Here we have true, we have true again, then true, true, true. Then here, negation of Q implies negation of P and R. Negation of P and R is here. Negation of Q, that is, we have to consider the opposite of this element, second element, with this one. So that true implies true is true, true implies false is we have to take the opposite, that's the negation, that is here, the negation of true is false, so that false implies true is true. The negation of true is here is false, so that false implies false is again true. The negation of this one is true, true implies false is false. This is true, true implies true is true. This is false, it is negation, that means true implies true is true. This is true, true implies true is again true, true implies true is again true again. Then true, that is this is false. The negation of false, false implies true is true. True implies true is true again, so that we have this one. Okay, then when we see the elements, that is the last elements, this and this one, we are comparing the equivalency of these two compound statements, so that as we clearly observe here, these two compound statements have the same truth values for the same assignment of their simple statements, that is true, 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 false, false, that is only their false at this stage. Therefore, from this, since they do have the same truth values for the same assignment, the two statements are equivalent, that is P implies Q or R is equivalent with the negation of Q implies negation of P or R. The next one, that is question number B, is again the same, that is these two are the same, the only difference is here, so that we can include the this one that is the one column for over the previous truth table. So that in this case what we need to include here is we have to include, for example, let negation of R and P be here over this negation of R and P. That is, we have R here and we have P here, so that the negation of this column must be connected with P by using that of conjunction. Therefore, the negation of true here is false, so that false and true is false. This is true, true and true is true. This is true again, true and true is again true. This is true, true and false is false. This is false, false and false is false. This is also false, false, false. We know that if we observe this column and that of this one, they are opposites. This is true, but this one is false, false, true, false, true, true, false, true, false, true, false. So that from this we can conclude that this is the negation of P or R, or negation of R and P is the negation of P or R. They are opposites. Then the last one, that is expected compound statement, will be this one, that is this column. Negation of R and P implies Q. So that in this case, negation of R and P is already calculated here, that is this column, and Q is here, so that we have to combine this column with respect to this one, that is Q, by using that of logical implication from here to this one. So that false implies true is true, true implies true is true, true implies false is false, this one that is false implies false is true, whatever the truth value for Q here is, because at the starting this one is already false, so that false implies true or false implies false is true. Therefore this is true, true, true and true. Then if we compare and contrast all the three component columns here, they do have the same truth values. Therefore, not only for A but also B, the statement that is P implies Q or R, I mean C, P implies Q or R is equivalent with, and the second one, that is negation of R and P. Negation of R and P implies this one, that is Q. Therefore, both and that of C are equivalent to each other, which are verified by using that of this table. Okay, the next question which is going to be considered will be question number 7. That is this question. What does it say? Let U be a universal set and let P of X and Q of X be open statements on the universal set U. Then we are asked just to show that P of X implies Q of X is equivalent to the negation of Q of X and P of X. So that in order to prove, or simply just show the equivalency of this one, we have a proof here. We know that P of X implies Q of X can be written as negation of P of X or Q of X, since P implies Q is equivalent with negation of P or Q. Then again, this is equivalent with, in order to have of this form, we have the negation of P of X or Q of X, because we know that negation of P is already P, a double negation. Then this is equivalent with, if we distribute this negation over this logical disjunction, we have the negation of P of X is, that is P of X, or must be replaced by using that of conjunction, but when we distribute this one, so that this is and negation of q of x, negation of q of x. Then they are equivalent with the negation of q of x and p of x. That is simply distributive property. I mean commutativity property. Commutative property of a conjunction. Therefore, they are equivalent with this one, so that p implies q, p of x implies q of x, and the negation of q of x and p of x are equivalent to each other. So this is the proof. The next question will be question number 8. That is this one on again quantifiers. It says determine the truth values of the following. We have about 5 questions here. If we start from the first one, if we are given this one, that simply there exists x, which is an element of integer, such that x minus x squared is equal to 1, or there exists at least one integer x that can satisfy this condition. Because so that if we observe that means this statement will be true if we can obtain at least one integer that can replace x and which can make this equation, that is x minus x squared is equal to 1. But logically, there is no any integer which can satisfy this condition, so that the truth value for this quantified proposition will be this one, that is false. Similarly, the second one, that is there exists at least one x or an integer x such that this integer is both prime and that of even. Therefore, similar to that of the first one, this will be true only when if we can get at least one integer x which is prime and even at the same time. So that in this case, this is the truth value for this one is true. For example, if we take an integer that is x equal to this one, that is 2, we know that x is prime number because it has only 2 factors, and it is also even because it is divisible by 2. Therefore, due to the existence of this component, that is an integer 2, so that this statement is true. The third one is for every x or for every integer x, if x is even, then x squared is even, then x is even. Here, this could be a true, or simply this statement will be a true because since it is universal, if for every integer x, which is an element of z, if the square of that integer is even, so that x must also be even. Or this statement will become false if we can obtain at least one integer x whose square is even, but x is not an even integer. But if we observe the property of this one or simple integers, the squares and the component, the single integer itself, that is x, if the square of the integer is even, so that x must also be even. Therefore, this is true, and it holds true for every integer whose square is even. The fourth one is there exists a real number x, which is an element of R, for every y, an element of R, satisfying this condition, that is x times y is equal to y. That means there exists a fixed at least one x or one real number x that can satisfy this condition for every real number y. So that because of this one, for example, that is totally this one is true, because if you take a fixed x that is equal, which is equal to 1, so that because we know that 1 is a multiplicative identity with respect to that of set of real number, therefore due to the existence of this one, that is fixed real number x equal to 1, whose product, that is x times y, is equal to y. The product of any real number by 1 is the real number itself. Therefore, this is a true statement. Here, for every x an element of R, there exists a corresponding y, an element of R, such that x times y is equal to this one, that's simply 1. So that this will be true if we can obtain a corresponding y for every real number that is x an element of R, satisfying this condition. But this one is false. By using that, if we take a counter example, if I take x is equal to this one, that's simply 0, there is no corresponding y which corresponds to this one, that's simply y, x is equal to 0, and that can multiply this one, that's simply 0, to give, or simply just to get this one 1. So that due to the existence of this real number, that's simply 0, which is an element of R, and because of the absence of any real number that can be multiplied by this one, that's simply 0, just to get 1, therefore this statement is a false statement. So that these are the truth values of these quantified propositions. The next one is question number 11. Question number 11, which says, consider the following arguments. Then after considering this argument, the question that follows from this given argument is that we're asked just to find, or simply just to obtain, the symbolic form of this argument first. And after obtaining the symbolic form of the argument, we're asked just to find, or just to prove its validity, the validity of the argument. And therefore, the question that I take from the worksheet just to consider will be the first one. It says, wages will increase only if there is inflation. If there is inflation, then the cost of living will increase. Wages will increase, therefore the cost of living will increase. So that wages will increase only if there is an inflation would be first premise. If there is inflation, then the cost of living will increase will be the second premise, and wages will increase will be the other, or simply the third, and therefore the cost of living will increase is the conclusion for this argument. So that in order to convert, or simply just to obtain the symbolic form of this one, let us represent the simple statements of this argument by using that of letters. For example, in the first case, let's assume that let us represent the first one by using that of P. From this one, that is, wages will increase if there is an inflation. So that from this, the first statement will be wages will increase. Then the next one, which is combined with this one again, there is inflation, that is, there is inflation. Next, from the next, or simply second, from the second premise, if there is inflation, that is, it is already represented here, then the cost of living will increase. So let R represent living will increase. Then wages will increase, it's already here. Therefore, the cost of living will increase, it is already represented here. So we have three simple statements. Then in order to represent each premises by using that of in symbol, the first one, that is A, will be wages will increase only if there is inflation. That is, if wages will increase, then there is inflation, that means. So that the first will be P implies Q. The next one, if there is inflation, means that is Q implies cost of living will increase, that is Q implies this one that is R, and the other is wages will increase, that is P. Therefore, the cost of living will increase. The symbol for therefore this one, the cost of living will increase will be this one that is R. Therefore, the symbolic form of this statement, or simply this argument, will be P implies Q, Q implies R, P therefore R. Then the next question that follows from this one is that checking the validity of this argument. So that by using that of informal proof, let us check whether this statement or simple argument is valid or invalid. So the proof will be, let us start from this one. We know that the first case, P is true, since it is a premise. Then from the first premise here, P implies Q is true. But in order to determine the truth value of Q here, already P here is true, so that for this logical implication to be that of true, from here we have Q must be true. The only possibility for the truth value of Q will be true. It's just simplification. The other is if Q is true again, the second premise, that is Q implies R is true. But here Q is true, so that if the if statement of the logical implication is true, the conclusion must also be true, so that from this we have R is true, which is the result. So that if we assume that all the premises are true at the same time, the conclusion that is R is also true. Therefore, from this we can conclude that the argument is valid. It is a valid argument. Okay, the next question will be question number 12. Question number 12, which is on the second part of the chapter, that is logic and set theory, which is related to that of sets. It says prove the following four sets A, B, and that of C. The first one will be if A the subset of B and B the subset of C, then we have A the subset of C. Then in order to prove the first one, for example, let's assume that A is the subset of B and B the subset of C. What we need to show here is, that is our claim will be, A is the subset of this one, that is C. So that in order to show that this one is derived from this one or simply obtained from these two, we can start by let X be an arbitrary point or arbitrary element of A. That is, X is an element of A. This implies X is an element of B, since A is the subset of this one, that is B. Again, because B is the subset of this one, that's simply C, so that every element of B must be an element of C. So that from this again, X is an element of B. This could imply X is an element of C. So that from this, as we clearly observe here, every element of A is an element of B, and again every element of B is also an element of C, so that every element which is an element of A is an element of C. Therefore, from this, for every X an element of A, this could imply X is an element of C. And this is the property for A to be the subset of this one, that is C, and the subset of C. Just so we can consider transitivity or other things. The next one, that is B. B, that means we have, let's assume that A the subset of B and B the proper subset of C. B the proper subset of C. What we need claim, or what we need to show here is that A is also the proper subset of this one, that is C. Therefore, similar to that